Good afternoon. My name is Rauwerda, as explained. I'm a business developer at Technolution, a company from the Netherlands. We are about 300 people doing systems integration. I also have an affiliation at the University of Twente, and I will tell you our story of RISC-V. Let me start with space. I believe there are some more people from space, so we will bring RISC-V to space. And if I talk about space, there is new space, which is small satellites based on commercial off-the-shelf components, no qualification, not radiation hardened. And on the other side of the spectrum, you have traditional space, the big NASA satellites, European Space Agency satellites, with onboard computer units, instrument control units for every instrument, everything hardened, everything certified, expensive. But in between, there is the new segment which is rising, which is called SmallSats. So it's actually new space, but with better performance, radiation tolerant, and many satellites will be shot into space. So that also means that higher volumes of electronics, and it means you have to be cost efficient. So the problems we see there is actually that nowadays in space development, every instrument is developed for space is actually a custom instrument development, which actually is custom for a certain satellite platform. And what we noticed from instrument developers for space is that they would like to have an easy way to integrate instruments into their satellite platform. There's also other problems. Data rate is not sufficient, or high data rates, data bandwidth is not sufficient. So you also need compression in space or intelligence in space, so that you can already reduce the data and only get the relevant information back to Earth. And we actually saw that there's not really any generic platform for instrument control units, so to connect instruments to spacecrafts. And then there will be the issue that multiple instruments are on the satellite, and you also have to protect the data of those instruments. So you need to do data encryption and take security measures in the platform. So after long discussions with the industry, with the instrument developers, with platform developers, we proposed a solution of having a modular electronics approach for new projects, so that with the modular approach you can share your costs and have a more cost-efficient solution. The modularity also reduces the overall build time of a satellite, because we now can isolate the instrument development from the platform development, and at the last stage merge them together. With the modular electronics, you can already do rapid prototyping, and our design is capable of building electronics based on radiation hardened component, radiation tolerant component, or even commercial off-the-shelf components, which are not hardened at all. So depending on the mission profile, you can choose what quality level you want. We have proposed this together with the Dutch Aerospace Center to the Netherlands Space Office, and with the support from ESA, we actually built a prototype of this approach, where we showed that flexible integration of instruments to a platform, a new space platform, satellite platform, is possible. And for Technolution, it was also very important that the modular electronics will also have a FPGA component in there, because the FPGA offers you a lot of flexibility. Now jump back a little bit to the past. So RISC-V at Technolution. We are already developing RISC-V cores since 2014, 2015. We're one of the founding members of the foundation, and what we do already since 1987 is we develop supplier-independent programmable logic designs. We do not only do the programmable logic design, we also do the electronics design, putting the FPGAs on an electronics board, And we can implement it for every vendor. That has to do with supply chain management, life cycle management. So to choose which component fits the best with the life cycle of a product. And for our security business, we had a need for our own soft processor that was 100% developed by Technolution, where there were no dependencies on open source or third-party hardware, so fully under the control of Technolution, that we could implement for classified security applications. And since we are working with different FPGA vendors, we would like to have a softcore that we can port to every kind of FPGA device. You could, for instance, in the past use a NEOS soft processor, but then you're limited or bound to Altera devices. You could use a microblaze soft processor, but then you're bound to Xilinx devices. So that was the reason that we supported the foundation of the RISC-V community and started the development of our own processor cores. The processor cores are nowadays used in classified security products. For instance, we have a line of secure line encryption products that are used by governments and defense agencies, where we run the control flow software on the RISC-V processors, and all the data encryption logic is, of course, in the hardware logic of the FPGAs. And this offers us, because we own the design, it offers us the full understanding of the implementation. But we can also show transparency to our customers or to the evaluation bodies, because it's developed based on an open standard. So everybody knows what the standard is and can evaluate against this standard. And as I already said, for lifecycle management purposes, it's very important that we can transfer or port the design to a different vendor, but still use the same hardware sources, still use the same software sources, still use the same compiler tools, which makes it easier for certification purposes. So we have actually two processors in our line, very simple microcontrollers, an embedded processor which supports the 32-bit instruction set, M&A, nothing more. We can run there on bare metal software like C or embedded Rust. We use a lot embedded Rust, which is memory safe for security purposes and reliability purpose, very important. We have ported FreeRTOS on our RISC-V processor, and we did also porting of other OSs for customers. And then we have an application processor with the supervisory mode implemented, so that we can also run a full Linux stack on our processors. And this is what we use in our projects. Now going back to the control and data processing unit, so instrument control logic for instruments in small satellite platforms. As said, we have good knowledge about FPGA designs. We have our own RISC-V processor cores, so let's also bring those RISC-V processor cores towards space. That's what we did. We built a prototype. This is actually a lab prototype, a picture of that, where we have some commercial off-the-shelf evaluation boards, and we designed our own interface board so that we can interface with space-compliant interfaces like SpaceWire, SpaceFiber, and we also have housekeeping data on board. That's actually the blackboard in the picture. What's then in the FPGA? In the FPGA there is a RISC-V processing system. We call it Frenox, so the RISC-V Frenox is in there, and we have extended that Frenox with an interconnect infrastructure, AXI4 compliant, with SpaceWire interfaces. SpaceWire is a serial link used in space environments, and SpaceFiber, which is a high-speed serial link. And there's also room to add accelerator extensions into the fabric, so that we can do, for instance, DSP processing, image processing, etc. And with this constellation, we can build a standalone instrument control and instrument data processing unit for the sensor. Then there is embedded software running on the RISC-V processor that does the telemetry and telecontrol data handling. It's at this moment bare metal, but it could also be running on an operating system. The proof is in the pudding. So we asked our friends in the Netherlands, Airbus and ESRON, the Dutch Space Research Institute, whether they had a real instrument on loan. We actually got an engineering model of a real instrument, and we connected that to our control and data processing unit, so our instrument control unit. That's the box in the middle. And we actually showed that we can control the instrument on the left, we can get data out of the instrument, and we can also do data processing in our control box and then send the data and the information to an emulated satellite platform. So this is actually showing the ecosystem of where we're involved in. We started the project for the Netherlands Space Office, where we showed that this concept of modular electronics works to control satellite instruments, to do data processing of the instruments. Inside the instrument control unit, we use RISC-V processors and other accelerator logic. We now have a proof of concept, and we are currently negotiating with some instrument developers, among others, Airbus in the Netherlands, but also Science and Technology, about an engineering model development of this concept. But in parallel, we're also involved in European research projects where we can extend the reliability and the security features of the architecture. We do that in the Tristan project, and together with our Dutch partners, the Dutch Aerospace Center, University of Twente, Irdeto, and with the support of the European Space Agency, we're looking to improve all kinds of aspects. Like, for instance, what we do with the University of Twente, supported by ESA, is that we are looking on a reduced RIRI interface, the RAS error record register interface, that has been defined by the working group. We are actually looking whether we can have a light implementation of that, because for embedded applications, as we see it, it's actually too large and has too much overhead. And we're also checking how we can use that for radiation testing purposes. At the University of Twente, they're doing research on checkers, so Trojan horse checkers, fault tolerance checkers, and also how we can set up generic radiation test environments. So in conclusion, as I said, for advanced electronics and embedded systems development, we master software, embedded software, electronics engineering, programmable logic or FPGA design is the glue between the software and the electronics. We can also supply supply chain management and lifecycle management services. We even have our trusted assembly lines where we can build trusted devices. But in the end, everything is about modular electronics. Modular electronics enable reuse and enable cost-efficient solutions for low-volume projects. Modularity gives reduced instrument development times and test times, and that's only possible if you to benefit from standardization, because from standardization, like the RISC open standards, you can benefit from transparency, portability, but also the flexibility. And that's what we do. Since 2014, we built high security and high reliability systems using RISC-V processors. Thanks for your attention. I hope it is clear. I also have a poster here in the outside, D14, there's a picture on here. So if you would like to catch up with me, go visit my poster or send me an email or a phone call or answer some questions right now. Thank you. Oh.
Okay, we do have time for one question.
then it was boring. Yeah, okay.
I can put one question. So, I mean, you have different flavors of the FreeNox, and you have the FPGA, which sometimes is very big. Have you at least experiment like deploying multiple versions and flavors of RISC-V cores, and then putting different functions in each of these cores and having this separation of concerns, which is highly needed in this kind of industry?
Yeah, so that's a really good question. Yes, we have experience with deploying multiple RISC-V processors in FPGAs. Without going into all the details, you can imagine, especially for security applications, but also for reliability applications, the separation of concerns is very important. So we never run multiple functions on one processor. So we have multiple processors, sometimes cascaded in the design. If you look at our family of processors, yeah, it's a small family only 2. It's small microcontrollers because the microcontrollers is actually mastering all the functions in the system. So we do not do high performance computing on there because we do all the acceleration in programmable logic cores. Yeah.
Thank you.
You're welcome.
Okay, so thank you very much again.